Imagine standing on Titan. Up close, Titan's surface would look frozen and unfamiliar, with water ice as hard as rock and dark methane-rich liquid nearby. Its surface temperature is about minus 179 degrees Celsius, making the ground extremely frozen. Titan is not a planet, it is Saturn's largest moon, circling the ring giant in the far reaches of the solar system. Titan has a diameter of about 5,150 kilometers, making it larger than Mercury but still smaller than Earth. Only Jupiter's moon Ganymede is larger, making Titan the second largest moon in the solar system. Titan travels with Saturn in the outer solar system, about 1.4 billion kilometers from our Sun, which is a G-type main sequence star, often called a yellow dwarf. Because Titan is so far from the Sun, only weak sunlight reaches it, helping keep the surface extremely cold. Titan's thick atmosphere gives it a golden-orange appearance and hides most surface details from view. Titan's atmosphere is made mostly of nitrogen, with methane and other gases mixed in. Through early telescopes, scientists only had limited information about Titan. Because Titan's haze blocks visible light, scientists had to use instruments to study what was beneath the atmosphere. Infrared imaging can reveal parts of Titan's surface that regular cameras cannot clearly show. False color images turn Titan's data into visible patterns, helping scientists study its atmosphere and surface. By combining different types of data, scientists can create a clearer picture of Titan's atmosphere, terrain, and surface features. Titan's surface includes dark hydrocarbon lakes, branching channels, and dune fields shaped by wind. This close-up shows how Titan's icy ground meets dark liquid channels across the surface. Methane on Titan can form clouds, fall as rain, and collect in lakes, creating a weather cycle similar to Earth's water cycle. Titan's low gravity would make movement feel lighter, so a step could carry farther across the frozen surface.
Weaker gravity lets astronauts leap far higher than they can on Earth.
A day on Titan lasts about 16 Earth days, because Titan rotates at the same rate that it orbits Saturn. 1 year on Titan is the same as Saturn's year, about 29 Earth years around the Sunday. Because Saturn takes so long to orbit the Sun, Titan seasons are much longer than seasons on Earth. Like water on Earth, liquid methane and ethane can shape Titan's surface by carving channels into its icy crust. Beneath Titan's frozen crust, scientists believe there may be a salty ocean, making Titan important for studying possible habitable environments. From orbit, Titan's largest dark seas can be seen near the North Polar region, where liquid methane and ethane collect in broad basins. Titan's shorelines may change over time, as wind and liquid movement affect the edges of its lakes. Titan's branching drainage patterns show where liquid has moved across the surface and collected in low areas. Launched in 1997, Cassini-Huygens made repeated flybys of Titan, using radar and infrared instruments to map the surface beneath the haze. Then Huygens plunged into the atmosphere in 2005, descending through orange murk to the frozen ground. Huygens sent back surface images and measurements, giving scientists their first direct view of Titan's frozen landscape. Together, Cassini and Huygens transformed Titan from a mostly hidden moon into a world scientists could study in detail. Titan's atmosphere is dynamic, with clouds forming and shifting above its cold surface. James Webb has observed methane clouds changing in Titan's atmosphere, adding new evidence for its active methane weather cycle. Titan's thick atmosphere creates a strange temperature balance, trapping some heat close to the surface. While haze blocks sunlight before it can warm the ground, heat is held back and sunlight is muted, leaving the surface deeply frozen. Then comes the central mystery. Sunlight constantly breaks methane apart high in the atmosphere. If nothing replaces it, the sky should eventually lose methane. Scientists therefore search for cryovolcanoes, ice volcanoes that would erupt water ice, ammonia, methane, and frozen compounds instead of molten rock. If Titan has active cryovolcanoes, they could bring icy material and gases from the interior to the surface, showing that Titan may still be geologically active.
What you're seeing now are actual images of Titan captured by NASA's Cassini spacecraft.
Antarctica and Arctic tundras are Earth's closest visual comparisons to Titan's frozen surface. Earth's frozen landscapes help us imagine Titan's surface, where ice, ridges, and hard ground create a harsh terrain. The comparison only goes so far. Earth's poles are brutal, cold, and dry, but Titan is colder, darker, and stranger than any frozen habitat on Earth beneath a dim and distant Sunday. Yet, even in such extreme conditions, scientists still ask one extraordinary question. Could anything survive here? On Titan's surface, any life would face extreme cold, weak sunlight, and rivers made from methane and ethane instead of water. Scientists turn back to Earth, studying organisms that survive freezing temperatures, dryness, and limited energy. Tardigrades and Antarctic nematodes can survive freezing, dryness, and long periods without food, showing that life can push against extreme limits. On Earth, methane-producing microbes called methanogens survive in low-oxygen environments by using chemical energy instead of sunlight. This makes scientists curious about Titan, where sunlight is weak and methane chemistry is everywhere. If anything lives there, scientists expect microbes first. Tiny bodies need less energy, hide in narrow pores, and survive where larger forms collapse. Possible refuges could include lake margins, icy cracks, or a speculated salty ocean beneath Titan's crust. In Titangent-like laboratory experiments, scientists study whether molecules can naturally self-assemble into tiny membrane-like bubbles in liquid methane. They are not cells, not proof, and not life. Yet they offer something important, a boundary, which is one basic feature living cells need. Imagine a microscopic world beside a dark hydrocarbon shore, where chemistry folds inward, protects itself, and repeats. If life existed on Titan, it would be very different from life on Earth. It would have to use methane-rich surroundings, extreme cold, and scarce energy as its rules. That is why scientists search for signals chemistry alone cannot easily explain. Methane imbalances, complex organics, strange microscopic structures. Each test raises tension. A positive sign could reshape what we believe life can be. No evidence of complex life has been found on Titan, but its chemistry, liquids, and extreme environment keep scientists searching. Did Titan's rich organic chemistry ever approach the threshold of life? The data glows across monitors, but certainty stays just beyond reach today. The answer begins with Dragonfly, NASA's car-sized rotorcraft designed to explore Titan from the air and surface. It will move through Titan's dense atmosphere like a careful explorer. Unlike a fixed lander, Dragonfly can fly from place to place. It will touch down, test the surface, and rise again, traveling across dark dunes and icy ground. Each flight will let Dragonfly compare locations shaped by different conditions and different parts of Titan's past. At each landing zone, the craft becomes a laboratory. Instruments unfold, sensors taste the air, and a drill will reach into frozen material that may have preserved organic compounds for long periods of time. Dragonfly will study chemistry, atmosphere, geology, and habitability together, asking how molecules form and change. Dragonfly will collect and study surface samples to learn how Titan's materials and chemistry interact in this cold environment. Before Dragonfly ever reaches Titan, scientists must carefully clean and test the spacecraft to reduce Earth-based contamination. Clean rooms, protective suits, sterilized parts, and microbial testing help make sure Dragonfly studies Titan's chemistry without confusing it with material from Earth. Dragonfly may not answer every question, but each sample could bring scientists closer to understanding what Titan's chemistry is trying to tell us.
T-minus 15 seconds.